So this is part 2 of global atmospheric circulation, and this is where it becomes a little bit more complex because we've got to factor in the idea of axial tilt, the fact that the Earth tilts on its axis, and so different parts of the Earth face the sun at different times of the year, and this can lead to the intertropical convergence zones, as well as different seasons at different times of the year in different locations. So as a recap, here is the global atmospheric circulation patterns that we drew in the last video. You can see you've got the rising air at the equator forming the Hadley cells as the air sinks towards the tropics, and this can lead to high pressure systems where the air is rising, leading to clouds and rainfall that we see here, whereas we get drier and less cloud, less precipitation in the areas of high pressure where the air is sinking. We next then have the feral cells, which goes up towards higher latitudes where it then meets the colder air coming down from the poles. The warmer air is forced up over the cooler air, forcing the air to rise and cool, again leading to high pressure and rainfall in these areas. But it isn't as simple as that. The Earth is on a tilt on its axis running from the north to the south pole. Now, as the Earth rotates and orbits around the sun, at different times of the year, different parts of the Earth are facing the sun. And obviously it takes a whole year for the Earth to orbit the sun all the way around it. So if we take this picture here, this shows that the Earth's axis means that the northern hemisphere, which is where we live in the UK and Europe, is tilted away from the sun. This means that the sun is shining at more of an angle as it hits the ground. This means that the solar energy is less focused, so there's less energy, leading to cooler temperatures. But also the days are shorter, so there is less time for solar energy. This means we get cooler temperatures throughout the day and throughout the night time. When we go 6 months later, as we've orbited the sun, you'll notice that now the northern hemisphere is tilted towards the sun. This means that the sun shines at less of an angle down here, therefore the energy is more focused, more concentrated, so there's more energy to heat the ground, and so we get warmer temperatures. But also the sun is out for longer, the days are longer, so there's more time for solar energy to heat the ground. The same is true in the southern hemispheres, but it's the opposite way round. This is why when we get winter in the UK, you will have the summer period in places like Australia and New Zealand, and vice versa in the winter. When it's summer in the UK, it will be winter in Australia and New Zealand. And the whole reason for that is down to this axial tilt. So if we return to our earliest diagram of global atmospheric circulation with the Hadley, feral and polar cells, this is what we drew. But now if we add in the fact that we now know that we have this axial tilt, and so what that leads to is this. So you can see that here, if the sun is over on the right hand side and the solar energy is coming from down here, we can see the northern hemisphere is tilted away from the sun. This means that this convergence zone, where the winds from the north and from the south converge, and we have this low pressure system which is now just to the south of the equator. And we can see then that this means that all of these cells are actually affecting different parts of the planet. And if we look when it's summer in the northern hemisphere, you can now see that the convergence zone, where these winds converge, and then we have the low pressure where the Hadley cells meet, is now to the north of the equator. Now on the image of the Earth that you can see here, we've got these different colours, and these actually can really show clearly the kind of ecosystems that occur. We can see around the equator, and to some degree north and south of them, we have this very dark green. Now this represents the tropical rainforests, and we know that tropical rainforests like hot year-round temperatures with lots of rainfall. Whereas when we move here into northern Africa, this area is called the Sahara, and what we can see is no vegetation at all. This is because the Sahara Desert is so dry. And the reason for it being so dry is it sits underneath this high pressure descending dry air. So we can see that the weather and climate is very important, not just for understanding the weather and climate, but also for linking into ecosystems in a later part of the course. So if we introduce this idea of the intertropical convergence zone, now this is where we know that because of the rising air at the equator, it leads to the wind being drawn in from the north and south to try and correct the pressure difference. As this is low pressure, the air fills in to try and equalize the pressure. So what that means is then we have these winds, but we know with the Coriolis force that these winds are deflected off as well. So we have this wind pattern going around the globe. But as we've already said, we know that the Earth is at a tilt. So what that leads to is actually this area of highest energy doesn't sit directly on the equator, but it can vary to the north and to the south, depending on the time of the year. And this is what is known as the intertropical convergence zone. Now on these belts, at different times of year, then where the highest energy is, you're going to have the most evaporation and the most rapid air movement and highest low pressures. So this is going to lead to the monsoon conditions, which is why we often get monsoon conditions in the summer months, because the higher solar energy driving the evaporation rates. So this intertropical convergence zone is also important because it will shift the impacts of the descending air of the Hadley and Ferrel cell meeting, and where the polar and Ferrel cells converge as well. And so this will have an impact on global weather and climate patterns. So now we look at what happens at the polar and Ferrel cell convergence area. And what we've got to remember is that we have the cold air from the poles up here, and then we have the warm air from the tropics down here. Now if you remember, we had the intertropical convergence zone, which goes a little bit like that. Now what this means is that we then start to get these ripples forming here. And so we've got this cold air which is coming down and trying to force its way in, and this becomes like a big battleground, because we then try and get the warm air trying to push up. And what happens is this wave pattern becomes much more complex, and it can go like this. And this is why in the UK we can see spells of warmer and colder weather within a few days, because this wave pattern will start to move from the west to the east. So the UK here will be in a cold spell, then the warm spell will come through, and then the cold spell again. But this will also link to rainfall, because where we have this meeting of the cold air and the warm air, this is where we're going to get rainfall. So we're likely to get rainfall where we get these edges here and here. Now this is a weather map that you might see at the start of the weather forecast. And it shows us the different rates of pressure, a bit the same way that the contour lines show us areas of equal height on a map. These lines are called isolines, and these join up areas of the same pressure. Now remember, where we've got low pressure, we have this rapidly rising air in the center, and then the air rushes in around to correct the pressure. And so this will mean that what we have is this quite strong winds towards the center of it. So often when we get low pressure mentioned on the news or on the weather forecast, it becomes known as having strong wind with it as well. Whereas the high pressure, where we have these isolines or isobars very far apart, then the air is stable and not much wind here. Now what you can also see though here is, here we have the zone of warm air around here, and we've got the zone of cold air here. Now what we can see is the warm air here has started to push in and try and get into the colder air. And where we have that, we have this warm front here. And this is where the warm air is being forced over the cold air as it tries to invade its space. On the back of it though, what we then have is the cold air trying to sweep in behind it. And this means that the cold air tries to force its way underneath the warmer air, again for causing the air to rise, leading to cloud and rainfall. So if we look at these simpler diagrams, here we can see on the right hand side we have the warm front. So in front of it here we would have the cold air, and we've got the warm air coming in and then rising up above it. So that means that we start off with cold conditions here, and then as this tracks through we then get to the warmer air in between. Now it doesn't mean it's going to be red hot, it just means it's going to be relatively warmer. And so you can see then that we go from this cold air with the rainfall, then we get the warmer air with showers. But here we can see where the cold air is trying to pincer underneath the warm air. Now this means that the warm air is forced up over it, again creating cloud. So we go through this cold zone to start off with, we then enter this warmer zone, we then get the cold front with the rainfall, and again we get another area of colder air. And so this can explain the changes in temperature and rainfall and weather we get associated with a low pressure system, particularly in the UK. And it can also explain at certain times of the year why sometimes when you have snow, that the snow will melt very quickly. And that is because the snow forms when we've got this cold sector, but then as soon as the snow has fallen, we enter this warmer sector and it all melts very quickly. But sometimes when we get the rainfall first and then the snow comes later, then it is much more likely that the snow is going to stay because we've got this colder air coming in behind it. Now this is very, very complex idea, and it's really an extension of the basic ideas of global atmospheric circulation. And these are the kind of areas that you want to be understanding if you are pushing for those higher grades of 7, 8s and 9s. Thanks for watching.